I think you should be able to see now. Yeah, in this talk today, I'm going to talk about the impact of interactions between individuals in this process of discovery, of innovation. And this interaction is going to be thanks to the complex networks and the usual tools of this this part of research. So I cannot, okay, now I can't. So basically in the first part here, I'm just going to introduce very briefly what you need to know. You don't need to know much, so it's going to be very brief. And then I'm going to explain to you this new model that we came up with and in some numerical results. And then at the end, we try to explain why we see all those things that we see there in the numerical results with analytical results. So the first thing we need to understand is what is an innovation process. So we all know that we discover something new, right? And it's something that happens to every one of us, even though it's not an innovation for everyone, but maybe we listen to a new song, right? So how can we describe this in mathematical way? Basically, it's some kind of discrete dynamical process that takes place in some space. So there is an individual that moves from one pattern to another. And so for him, the innovation or a discovery occurs every time the individual stops to a point that he has never seen before. Okay, so in literature, there is a difference also between innovation and discovery, because an innovation is something that is new for everybody, while a discovery is something that you discover just for yourself. Like, for example, when you listen to a new song, but the song maybe has been there for 10 years. So now, how do we study these processes? The way we usually do this is we record all the steps in a sequence, let's call it S. And so with this sequence, we can describe the whole process. Doing this in different contexts, like various contexts, with empirical data, many statistical laws have been found, and some of them now have also some analytical backup. But the most important one for this presentation is called Heap's law by Heaps. And it's just a correlation between the number of different elements that you can see in a sequence of elements. So basically, if you have a sequence of size t, so you count how many different elements you have, so the set. And so the Heaps law says that if within innovation process you have that d of t goes like a power law behavior, so t to the power of beta. So of course, beta has to be between 0 and 1, obviously. And this is called Heaps exponent. It represents our discovery rate. So the higher it is, the more we discover. And different models in the past have been trying to simulate this process with more or less success, depending on what the point of view is. And you can see here that many lists and many different approaches, from the urns, also some also random walks, and some other models from economics or biology. But here we're gonna focus only on one. This came out in 2014. It's called the urn model with tree green. I'm gonna show you this because it's at the base of the model I'm gonna propose later. In this model, it's like a toy model actually, and there are two basic dynamics. So what you do is that every time step, you draw from an urn that is initialized at the beginning with some colors, and at every time step you draw a ball from this urn, and you record the draw. So the event is the draw of the ball, and so the event is just the color of the drawn ball. Every time step, so you have a reinforcement of the color. So you just add the same number of the raw copies, in this case, of the same color that you just drawn. So this reinforces, and so there's a dynamics called rich get richer. So in the end, the gray color has higher probabilities of being drawn. So it's reinforced in our memory. And the other dynamics is the addition possible. This is the new part of this model, because the reinforcement model was already there. It's called urn polya, the polya's urn. And so here, what happens is that whenever we draw a new ball, a new color of a ball that we've never seen before, so no red here until here, now we draw a red ball. So not only we add the reinforcement, but also we trigger some new colors. So some new colors, in this case, new plus one balls of new colors are added to the urn. And basically, this means that, like, for example, whenever we listen to a new song, maybe it's a new album, and maybe this triggers the possibility of drawing some, of listening to some songs that are very close to that one. So that's why it's adjacent possible. So we trigger new possibilities that are close to the one that we just drawn. And from here, we can identify the Hipps law also analytically. The Hipps law is verified also. Depending on the parameters, we can span the Hipps exponent from 0 to 1. So it's great, everything's fine. But the problem is that here we have only one urn. We have only one individual, while here in this work, we wanted to study the interaction, the effect of interactions on this discovery process. So what we did is we coupled these urns through a network. So we consider a network. Here you have a representation of a network. It's called the Zachary Card Club. It's very studied in complex networks. Don't mind the colors for now. So you have this network, and this represents the social network. You have you have the nodes that represent individuals, and the links that represent the interaction, the relationships. So the model is really simple now, and it's not too much more complicated than the one before I showed you just before. So every node now has a NERD model with triggering, eventually with different parameters, but actually they're gonna be in this presentation they will be always the same. But so everyone has his own urn. So the urn everyone has is different. It's of course initialized with some number of balls of different colors at the beginning. But the important thing now is that the extractions that happen in all the urns are actually from an enriched social urn. We call this U tilde I. So this social urn, it's basically the urn of the I, the node I, so the balls in this own urn, but also we have an enrichment through the social links. So we also add in this enriched social urn the balls of the urns of the neighbors, but without the reinforcement. Okay, so this is everything that basically we need to know from the model. So we initialize and then we draw from these balls, and of course they are on model with triggerings. So every time we put the reinforcement, every time we discover something new, we have the triggering of new possibilities. So here we have a brief representation of what happens in two nodes, an example. So basically you have, for example, here at time t, you have these two urns. You have a link that goes from node 1, node 2. And for example, let's say that they draw a red ball and a blue one respectively. So they are reinforced. You can see here that they are reinforced. So this is the first dynamics, the reinforcement. And also, since it's new, because in the sequence it was new for them, they never appeared the red and the blue one before. So we trigger, so it's a novelty, and we trigger some new possibilities in the adjacent possible. So we add these two balls here and these two balls here. But also now at time t plus 1, when you draw from node 1, we also draw from the social enriched. So we can also draw these dotted balls, which come from the node 2. So there are these two here, one. So this is what I mean with the social enriched urn. Okay. So now we want to study what happens to the discovery process, right? So to the Hipps laws. What do we need to do so is to determine the Hipps law, and of course now we want to simulate the model and try to see if we can say something analytically. So we need a master equation for this, and here so the master equation usually it's something like the something from statistics, comes from, and it's something like for each node I, you have the variable d or t plus 1 is just the same variable times t plus the probability that this variable increases of 1. So that is that you draw a new ball. And it's basically so the number of colors in the social enriched urn that are seen by eye, this is important, divided by all the number of balls. So we have this little formula here that represents what I've just written here, but basically the same thing, where S is the sequence. And we can calculate this, okay? So, and maybe, I don't know how much time do I have, probably I probably need to skip this, but as you can see, we can write down an approximation of what will be the number of balls in the urn, and it's number of balls from his own urn, and that with tilde will represent the enrichment. So this is the number of balls, and these are all the social enrichments. So for all nodes in the graph, multiplied by the adjacency matrix. So this only counts for the neighbors. And these are all the colors that are inside their urn. So, and we can write down this in a different way, more fancy. But basically, in the end, we can calculate the formula before. Writing down here in the bottom, we can write the master equation in its continuous approximation. But here it's the same. So we have this differential equation, and then here on the top we have the number of colors that are never seen before by eye in the social enriched urn on the top, and on the bottom the number of balls, the total number of balls in the urn. And so you can see here that these equations is a system of equation, and it's actually nonlinear and also are coupled together through these coefficients here. That come from the adjacency matrix of the graph. And so, yeah, I mean, for now, like this, we cannot actually solve it. So in the first moment of our research, we just did a numerical solution of these equations using numerical methods. And we simulated, of course, the model with the urn with Python. And for example, here we have an example with 4 nodes and 3 links. And you can see here all of the nodes have the same parameters. So they are basically the same apart from these enrichments. And you can see here that so in the points are the simulations and the lines are the numerical solutions of the equations. You can see they pretty much fit. And you can see here that the node 1 that is enriched has a higher Hipps exponent, a higher rate of discovery. And if you estimate the Hipps exponent, so their discovery rate, you can see here that node 1 is actually very higher. But interestingly enough, although the other 3 never change, node 1 change. So this is strange, and we don't even know what will be the number that is gonna like if it comes down to 0.5, which is this number here, or if it stays up, or how much time does it take. We don't know all that. For that we can only use analytical solutions. Here it's just show you very briefly there are 5 different graphs, very simple, and just to see that there are different behaviors depending on the topology. So the topology affects a lot. Sometimes also, like for example here, the exponent diminishes and then here increases. Here are all the same. It's very strange. So we need to understand what happens. So before going to the analytical, let's continue with the numerical solution with more the bigger networks to see what happens here. For example, let's get back to the Zachary Carter Club network. And here, now I can show you that the color is just a representation of the Hipps exponent. So the bluer the color, the higher the exponent. And so you can see here that there are 2 nodes in particular. There are node 1 and node 34, which are the most important, most central nodes in the network. In fact, They are the instructor and the administrator of the club. And so, yeah, they have a lot of links, if you can see here. And so they have the higher exponent, while instead, for example, 17 is very far from the center, if can be defined. So yes, not too many links, and is in fact with low Higgs exponent. So very interesting, but you can see that now Higgs exponents change, as I said before, but the ranks persist. So this is the first thing, the first clue that something here is going on that is much more than just what I just told you. It's much more related to the structure of the network. In fact, for example, here we studied the Higgs exponent, the correlation between the Higgs exponent simulated at time 10 to the power 4 on the x-axis, and on the y-axis at time 10 to the power 8. And you can see that, okay, the number are different, so the distribution are different in all the cases. So these are 4 networks. The first one is Karate Club, and the other 3 are different and much bigger networks, and directed and undirected, doesn't matter. But the rank, so if we rank them from the first one to the last one, the correlation between the ranks is 1 in all cases. So yeah, there must be something behind this that comes from the structure. So now we move on to the analytical part, this last part. So this was the equations that we wrote before, and they seem very complicated to be solved. So what we can do is we can do some approximation. For example, we can get rid of these M zeros, depending on the parameters, but in a valid range with parameters, we can also approximate the denominator to just rho t and see what this can bring us. Okay, so this is much simpler now, because now, for example, using a more compact form like this, we can write down this as a sum of 2 matrices. We can write the system like this. So we have this, I is the identity matrix, of course, and A is the adjacency matrix. And so we can call this matrix M, and it's just a sum of the adjacency matrix and adjacency matrix times 2 numbers. And yeah, now this is much more simple to be solved. In fact, just with a change of variables, we can solve that. And in general, the solution to that approximated system, it's something like this. Okay, so where we have here, we have all the eigenvalues, lambda, we call lambda the eigenvalues with multiplicity ml. And so depending on the multiplicity, some logarithms appear here. Okay, so if the multiplicity is 1, here we don't have any logarithm. So logarithms appear when you have higher multiplicities, and then you have just some coefficients here. So in the long run, so asymptotically, this solution here are governed by the leading term, and we can identify easily the leading term just by considering for each of the nodes where the coefficients are non-zero. We take the highest eigenvalue, the highest p, for which the coefficient is not 0. Okay, so different nodes may have different lambda capped and different pi capped. Okay, so in general. Okay, this tells us something, because like the Higgs laws are kind of confirmed, because you have here the ddt time, it's something like a power law. It's not precisely a power law, but it's very similar to that. Now you can do this with some small cases, like for example the 2 nodes that will link from 1 to 2, and without going into the details, you can do all the steps. Probably I don't have the time to, so I'm going to skip this. But in the end, you get the solution. For example, here you have that, just looking at the solution, that the node 2, which doesn't have any links, is just a power law, while node 1, which has the link, is not only the power law times also a logarithm, okay? And you can repeat this for more difficult parts. For example, for a chain, and you have that the higher you are in a chain, in an open chain, the higher the exponent of the logarithm, but still the exponent here is the same. Okay, so this is strange. Just one other simple example. For example, for cycles. Okay, so you have a cycle and it's closed. It's let's suppose that it's directed. And here, if you do, it's very simple this to be solved because you can use symmetries to solve this. And basically here you find that now the solution is a power law with a higher exponent. Before it was nu divided by rho. Now it's 2 times nu plus 1 divided by rho. So very a lot higher. It's significantly higher. So what does this come from? So the reason for all of this comes from the strongly connected network. So this is the most important part now. So if the graph G is strongly connected, so for example, if it's undirected, it just means that it's connected. It means that you can go from every node to another one in a finite number of steps. So this means that the adjacency matrix is irreducible. And so the Perron-Frobenius theorem holds. And this theorem it applies basically to these irreducible matrices and tells us that there is an eigenvalue, which is positive, and in its absolute value, it's greater or equal than all other eigenvalues. Okay, so it's the maximum one. But not only this, it's also simple. So it also, the multiplicity equal to 1, and the eigenvector has all positive entries too. Okay, and this in fact is this eigenvector, for example, is very famous in complex networks because it's called also the Bona's eigenvector centrality measure, and in fact it accounts for local and global structure of the network. So this now can be applied to our case. In fact, we can apply this to our adjacency matrix because it's irreducible, and we can do the same to M because it's a linear function of A and the identity matrix. And so what you have that is if you have an eigenvalue, in this case, for example, the maximum eigenvalue, then the function of the same eigenvalue, so it's the same function that defines M, is also the highest eigenvalue of M, and also has the same positive eigenvector U. So this is great because now we know that if you remember the general solution was with the sum with all the eigenvalues. Now we know that there is an eigenvalue that is greater than everyone, and it is simple, so there are no logarithms, and all entries UI are all positive, so there are no zeros there. So now the approximated solution at the asymptotic time to infinity is just this. So this means that in this case you have that the exponent, the Hipps exponent is a function, a linear function of the maximum eigenvalue of the adjacency matrix times some parameters and depend also on the eigenvector centrality. So in this case, the only thing that changes the eigenvector centrality, in fact, for the Perron-Frobenius theorem network, for the Zachary-Carter Club network, you have that if you color the nodes according to this eigenvector centrality, you see that this graph on the right is colored very similarly to the network that I showed you before with the exponents. And in fact, on the left, you can see we plotted here a scatter plot between the Hipps exponent and the eigenvector centralities, and the Spearman correlation is almost 1. So great. So in fact, so we now know that the Hipps exponents, the discovery rates, depend on this eigenvector centralities, even though it was a result that we found with some approximations. But it's something that actually is there in the simulations. And just final result is that, okay, what happens to non-strongly connected graphs then? So in that case, you can do a similar approximation for getting the solutions, and you can basically inductively find an algorithm that finds all the eigenvalues for all the weakly connected components. So you do this algorithm, and then what you find analytically is that now the correlation is not with eigenvector centrality, but with the alpha centrality, which in literature is just an extension of the eigenvector centralities to directed networks. And in fact, the alpha centrality is important just before this vertical line. Okay. In fact, you can see that the correlation between the beta and the eigenvector and the alpha centralities in these 4 cases, which are the 4 big networks I showed you before, it's almost 1. So this is a great result because the simulation were very big. So just to conclude, I think time's up. So the important thing about this model is that it's the first model where urns are coupled together through a social network to study the interaction of discovery processes. And maybe there are something, it's very simple. In fact, there are some things that can be improved. But this is the first also time that the concept of a social urn is introduced in this context. And this, in fact, enhances cooperation, as we've seen, with the higher exponents. But all in all, it's a simple model, and we also have analytical solution. So we have an explanation for the things that we see. And in fact, we know now that these rates of discovery, at least for this simple model, are related to topological properties, which is something that is also been found in the data and empirical data. But now what we can do is take this model and make it maybe more realistic, and maybe compare it to also empirical data. And for example, what just already we are doing, we can study optimal team structures, or for example, we can include higher order type of interactions. So like simplicial, with using different kind of interactions, like simplicial complexes and other more fancy stuff. So with this, I thank you all, and also want to thank my collaborators for this work, Jacopo Jacopini, Enrico Baldi, Vittorio Loreto, and Vito Latora. And if you want, you can find the paper out in PRL. So thank you. If you have questions, of course, I'm happy to answer that then.
Thank you.